All right, so in this module, we're going to continue talking about the different silicate structures and hopefully be able to predict structures by looking at the last category, which is when the oxygen to silicon ratio is the highest it can be, 4, right? And so if you think about the isolated tetrahedron, that's SiO4. So that's the ratio there. So this implies that there's no bridged oxygens and they're all non-bridging. So in essence, these types of structures have an isolated SiO4. And if you're wondering what types of structures compose these, it's those where they have so many of those alkali earth metals, those other free, they act as free ions, they're not part of the network, and they surround completely, right? So we have enough of those additional cations where the tetrahedron is isolated. So as you can see in this structure, the tetrahedron is isolated, and then you have all of these other cations surrounding those networks. And so this is an example of the olivine structure where you have that phenomenon. You'll always see that, in those types of structures, you'll see the SiO4, but then that charge has to be balanced in some way. So here are some of the, either with magnesium or lithium or something like that. And that's what we have with these. So that's what you would expect with this type of number. So let me show you an example of that. And in the ionic structures in the complex, I showed you spinel, and I showed you an example of lithium manganese oxide is a spinel structure, and it's a lithium ion battery cathode. So since we're talking about isolated tetrahedron, and we're talking about the olivine structure, I thought I would also bring up another class of lithium ion battery cathodes, and that's the lithium iron phosphate. So we've been talking about silicates. This is a phosphate, so it's P instead of Si, but it's the same idea. And so this is the olivine structure. And you can see that there's tetrahedral and octahedral sites. And again, they're all isolated. And then the gray ions you see here are the lithiums. And you can see all the lithium ions are kind of quote unquote free. And they form in linear pathways, right? So down kind of these pathways, you can see a linear chain of lithium. So this is what, again, gives it the ability to remove and add lithium into these pipelines of lithium. So that's how they diffuse. They diffuse in and out of these tunnels that you see. And so again, this structure is similar to the lithium manganese oxide in that the diffusion occurs in the linear directions of 1D. And so it's relatively slow diffusion compared to some of the other structures in batteries. But again, it's a little safer. One of the ways that people have gotten around the sort of slow diffusion based on these linear kind of pipelines is that they make this lithium iron phosphate really small. So if you make nanoparticles or things like that, then the diffusion distances are shorter because the particle is smaller. So it's not as big. And so that's one of the ways that we can use the olivine structure and, again, lithium ion batteries, cathodes. So unrelated to the olivine structure, but since we've already talked about the other two main classes of battery materials, I thought I would show you sort of the state of the art. And that's what's known as the layered structure. So this was the first one that was found in the rechargeable lithium ion batteries. This was the first cathode that was widely used, and it's the lithium cobalt oxide. And it's a layered structure. So in this, we see the octahedrons for the cobalt, and then we see the lithium here, and we kind of think of them as in these. So we basically have layers of the cobalt oxide, so that's all the blue, and then in between we see layers of lithium. And so this structure, compared to the one we just saw, right? So this has a linear arrangement of lithium. This has a planar, right? So instead of having to go down one pipeline, the lithium can diffuse out anywhere in the plane. So it makes it much faster. So this was the first one that came up that people came up with. And in fact, my academic grandfather, Dr. Goodenough, came up with using this material for lithium ion battery cathodes. And again, it's because we have the planar structure here And lithium readily diffuses out of the structure, making it really fast to charge and uncharge. That makes it a really good material. However, if you remove too much lithium, this structure can collapse. And those are some of the problems with this structure, is that if you take out too much, you're just left with cobalt oxide. You kind of collapse the structure, and that's where some of the issues with overheating and so forth can come in. So we have to be careful with how much lithium is removed, and so that's one of the limiting factors with this structure. If you're wondering what's in your cell phone or whatever, it's probably some version of this. Most of the new cathodes are this layered structure, but they may have more than cobalt. They may also have nickel and manganese and so forth. So they tend to be a little bit more complex, but they're still typically based on this layered structure because the diffusion and the charge rates are so fast.